Hello, everyone. My name is Timothy Lee Grant, and today we are going to be continuing our journey on learning heaps. So, targeting heaps, trying to get good at them, trying to understand them. Let's go! All right, so we're going to do a randomized medium. So, just close our eyes, pick the closest medium that we see. All right, here we go. Okay, this one. The closest medium is path with maximum probability. All right. So let's start this. 1514. Path with maximum probability. You are given an undirected weighted graph of n nodes, zero indexed, represented by an edge list where edge of I is AB, is an undirected edge connecting nodes A and B with a probability success of traveling or traversing that edge success probability of I. So the I's are connected on this edge has this probability, and there's I think so there's two lists. There's this edge list and this success probability list. There's a lot of arguments that were given. Okay, so minimize myself. Come on, there we go. Okay. Okay. So we're gonna have to look into those. Given two nodes, start and end, find the path with the maximum probability of success to go from start to end and return its success probability. If there is no path from start to end, return 0. Your answer will be accepted if it differs from the correct answer by, at most, a small number. Okay. All right. So, upon first reading this problem, I know that it's something to do with graphs. We have nodes and edges. These nodes are connected to other nodes through edges, okay? And we're given a list of integers, right? So, okay, how does that and by looking at the example below, we'll be able to solidify this a lot more. But right now, I'm just trying to think it over in my head right now before I go and actually try to make concrete understanding of what the problem is saying. So we have a list of int. Okay. Now, list of list. So edges of I. Okay, so what does that I represent? I represents the I just represents an edge. Yes. So each list in that list of lists is going to be one edge. Okay? And then within that edge, it's going to be connected to nodes A and B. So, okay, like 1 and 0, I think, for example. And so that's how you know that node 1 and node 0 are connected. And then let's say that this edge is the first. I think that it can appear any index in the edge list, but let's say that it appears at the 0th index of this edge list. So then the corresponding edge probability or success probability is also going to be at index 0, and it's going to be an integer representing the probability of traversing that, which will be 5. Okay, let's now look at the example and see if that's accurate. So, I want to know the edge between 0 and 1, which Oh, is at the 0th index, okay. 0, 1 has an edge. Now, in success probability, it should be 0 0.5, 0 0.5, the first index. Okay, so that actually does check out. Okay, so the question here is going to be, we understand how to, like, what the problem is asking. We want to start at a specific node and we want to end at a different node. And do they have more complex graphs? Not really, but like we want to start at this node and then come all the way up through these different node networks and then this one and then finally get to our end node. And we want to maximize the probability of success. Okay. So definitely not immediately clear to me how to go about doing this. I know that there are different like graph traversal algorithms, and I haven't gotten to those because this isn't. We did depth first search, which technically is a graph traversal, but I know that you. What was it called? Like Kringle's algorithm or something like that. There. I took data structures like what 3 4 years ago. I remember that there was a traversal one where you're trying to go from one node to the other node in a weighted graph. Trying to remember how we do that. It wasn't depth first search because depth first search isn't like targeted. You're not trying to go from one node to another one specifically. You're kind of, it's more of like a graph exploration, right? Like breadth first search, depth first search are more like exploration. But I remember that there was one algorithm that was used that was specifically used on a weighted graph, and the purpose was to minimize the cost. And what I can do is I can just take all of this success probability. No, I was thinking taking the success probability, making it negative because I want to minimize the cost. But what if I want to maximize the cost? But then it's just going to go back and forth. Although, possibly what I could do is take this probability of success and turn it into probability of failure. So, the probability is 1. And now, if the probability of success is 0.2, then the probability of failure is 0.8. So I can just do each element in this probability of success, turn it into the probability of failure by doing 1 minus it, and then I can try to minimize that cost, right? I want to minimize the probability of failure. Okay. And then I do the traversal. but I don't know what that traversal is. I think that's a question that's not going to be answered by me just like thinking. I remember it's something about traveling salesmen and Kruskal's algorithm or something like that. But I just remember those names, so that's not something that is going to be solved by me just sitting here. That's spinning my wheels, that's wasting energy. So let's go here. Um I also remember you can't have loops or did it have to be like a directed acyclic graph, a DAG? And this is not a DAG. This is undirected because you can go back and forth, back and forth, back and forth. Okay, so I remember in my algorithms class an algorithm to traverse from one node to another node using the minimum cost. Do you know what I am talking about? Okay, let's see what it suggests. Dijkstra! Yes, I remember this name. Dijkstra's algorithm. Oh, isn't this fun? Like, we thought that we were going to be doing heaps, and now all of a sudden we stumbled upon Dijkstra's algorithm. Like, learning new things or relearning, because I 3 years ago I did Dijkstra's algorithm. I can't remember what it is now, but yeah, this is kind of the fun of doing these LeetCode kind of videos is that you start one problem and then you realize that you have holes in your knowledge in so many other areas and you're able to just kind of like try to fill those in and eventually get better and better and better. Now we're going to be able to do graph traversals at the end of this video. That's going to be another tool in our toolbox, and then next time when we see another graph traversal, we're going to be able to understand it a lot better. So awesome. Let's go. So sounds like you're referring to Dijkstra's algorithm, which is commonly used to find shortest path from one node to another in a graph. Yep. Particularly when edges are not particularly when edge weights or costs are non-negative. So yeah, we have non-negative, and that's why I said I don't think I can negate them. So here's a brief overview. Start with a set of vertices and an initial node. Okay, so I have a set or a list of vertices. Yes. And an initial node, yeah. Set the initial node's distance to 0 and all other nodes' distance to infinity. Okay? Make all nodes unvisited. Set the initial node as the current node. Okay. For the current node, so now this part was the setup. So we set the vertices. We have the initial node, the distance is 0. And then all the distance to all of the other nodes is infinity. So that's the initial setup. And then all nodes are unvisited. Okay. So now we start the traversal, try to get from the initial node to the end node. Okay. For the current node, consider all its unvisited neighbors. Now, when it says that, there's two things that I'm trying to do right now. Number one is I'm trying to read this and understand Dijkstra's algorithm and how I can do it. The second thing is like, okay, well, how do I actually apply it in my particular instance? Because I'm given this list of two edges, but am I going to have to traverse each element in the edge list, then check, like let's say I'm at node 0. Do I need to check every single element in edges and see if 0 exists in that element? It would be much easier or much more time efficient if I had like an adjacency matrix or something, and I was able to just check all of the edges that are connected to 0. Because I'm going to have to check this for every single node, right? So just trying to think about how I might be able to transform my data into a format which is conducive to performing this algorithm. Okay. So for the current node, so I'm at the initial node. Consider all its unvisited neighbors. So I have to look at the neighbors which are connected to the node and look at which ones are have not been added to visited. Calculate their tentative distance through the current node. Okay. Calculate their tentative distance through the current node. So I'm at my current node. And so I just add that distance, right? So it's the weight of that edge. Compare the newly calculated tentative distance to the current assigned value and assign the smaller one. So currently all of them are infinity. So I'm always going to change it. But then if I get a smaller node, if I get a smaller distance, I'm going to update it again. But I'm noticing that it says like I have to visit unvisited neighbors. So now if I add that node as a visited neighbor, I'm no longer going to check it for its distance, right? So it's almost never going to be updated again. After considering all of its neighbors of the current node, mark the current node as visited. A visited node will not be checked again. Okay. Oh, no. I'm checking the node that I currently was at, not the node that I'm looking at, not the edge, or not the... Like, I'm at my current node, I'm taking my little binoculars, and I'm saying, oh, I see node 3. I'm at node 0, but I'm connected to node 3. What's my distance? And then I assign a distance to 3, and then I go look at the other one, but I only visit the one that I'm currently at. I'm only visiting 0, not 3, 2, and 1, which I'm connected to. Okay. Select the unvisited node that is marked with the smallest tentative distance and set it as the new current node. Okay, so then I just visit. Ugh. So then I just visit the node that has the current lowest value, because all of the unvisited ones are infinity. And so then I just check like, okay, this node has a weight of whatever, 0.2. So I'm going to go visit that one because the other ones have 0.5 and 0.7. So I visit the one with 0.2, and then I do the exact same thing over and over. I just check like all of the connected, updating them. Okay. Select the unvisited node that is marked with the smallest tentative distance and set it as the new current node. Repeat until all nodes are visited or the destination node's shortest path is found. Okay. The algorithm completes when the shortest path from the initial node to all other nodes is found, or the shortest path to the specified destination is determined. Okay. Now to actually try to code this up. I guess where I can start. I guess I can create like an adjacency list based off of these edges. Okay. So what I want to do is eventually I want to create a list kind of like this, where I have a list of lists, but instead of this value I, so like this one, I don't want it to represent that like node 1 is connected to node 2 and node, I don't know, node 1 is connected to node 3. I don't want kind of like this, where it just gives me a bunch of connections. What I actually want is something kind of like this, where I have a list, and now this node here doesn't represent an edge, it represents node 1. And now I just say all of the nodes that node 1 is connected to. So node 2 and node 3, right? Like node 1 is connected to which nodes? Well, there's a connection to node 2 and a connection to node 3. Now, what about node 2? Node 2 is connected to node 1. So node 1, and it's only connected to node 1. Node 3 is only connected to node 1. So this is what I want right here. This is what we have. So we're given a bunch of lists, or we're given this, which just represents a bunch of edges. And we do need that information because that information, the index of each of those edges corresponds to the probability. So I do want that. But I I also want this right here, where I'm able to easily index and figure out which node is connected to which one. But then how do I quickly, like, how do I quickly determine if how do I quickly determine the success rate? Because I don't want to traverse this entire thing find the index that it's at, then have to go to success probability and go to that same index to find the weight of everything. So maybe an adjacency matrix is in order where I actually have like I don't know, -1, -1, -1, and then 4, and then what was the oh, trying to remember how adjacency matrices. I remember you have up here. It's like node connected, like. So node 1, node 1, node 2, node 3, and then you had node 1, node 2, node 3, and then is node 1 connected to what? Node 1. And yes, it is. With a cost of 0 or something like that. Is node 1 connected to node 2? Yes, it is. And then you put the cost there. So I think this is what we actually want. We want this adjacency matrix because we need to store information about the cost between each node. We don't just want to know here that, oh, node 1 is connected to node 2 and node 3. We want to know like what the cost is. And then we can just like kind of go down this column and say, okay, I'm at node 1, I'm going to visit it, and I'm look at every single one that it's connected to. And I also need some way to like determine if it's not connected. We'll figure that out as well. But anyways, this is also pretty cool because, again, I thought that we were going to be doing heaps. And now all of a sudden we are natural. We're not just reading a textbook about what the difference between an adjacency or an edge list here, an adjacency list here, and an adjacency matrix here. We're not reading a textbook and it just says, oh, here's the difference. We're like trying to think through, like, okay, I have this. Oh, I can create this. Does this help me? No. Well, why not? And now we're able to understand significantly deeper, like, what these data structures actually help you with. And I'm out of coffee, but I have some water. So, I mean, we're kind of lost in the weeds, but this is an amazing problem because we're learning so much and we're getting like not that textbook just reading a definition of these graph traversals or this data structure for storing graphs. We're able to actually understand it. And now going forward, if I get something that is a weighted graph, I'm going to be more like, okay, well, I remember I needed to use an adjacency matrix last time. Does it still fit this same like template? If so, yeah, then I'm just going to use an adjacency matrix. I'm not going to, it's going to be much more natural and I'm going to understand it significantly more. Okay, so let's do this so we kind of get that out of the way. Now, here comes the thing that we need to try to change this edge list into that adjacency matrix. So for, what do I want to do? First I want to create a list of lists. So adjacency matrix equals a list. Now in this list, I want to have lists for in range in, right? So I want to create a matrix. I want to have a list of lists that's a two-dimensional array. And in that list, what do I want to initialize everything to be? I guess I can, because we know that it's not going to be negative, I can initialize it to -1, and that way, if I see a negative number, I just like I know that it is not connected. There is no connection. So initially everything is not connected, and then I'm going to go through my edge list and update this value to be the actual weight. Okay, so now I have my adjacency matrix. Now I want to actually go through my adjacency matrix and update the weight. So for Alright, so I am going through each of the edges. And now I need to update my adjacency matrix. So adjacency matrix, and then it's going to be a two-dimensional array equals in enumerate or something like this, because I also need the index. I think that is the right syntax, where you do enumerate and it gives you the value and the actual index. Is success probability of I. Okay. So edge of 0. Alright, so this is what I'm thinking about doing. So I have my adjacency matrix, and it is a two-dimensional array, and I'm going to update. So each time I iterate through edges, I get one of these, which is like 0 and 1. So I know that node 0 is connected to node 1, right? So I know, okay, well, let's just do this one, like 1 and 2. So I know that node 1 is connected to node 2. So I'm going to index this right here. So row 2, column 1, node, so 0. This is going to be 1 right here, edge, which is edge right here, is going to be that list. Now I index it at the 0th index, so I get 1. That's my row. Okay, so row 1. Okay, and then column at the second index, which is 2, column 2. So node 1 is connected to node 2. So now I'm working here, and what is that connection? It is the probability of success for that particular index, which is that edge. So that's, I'm going to be updating that to like point, in this case, I'm going to be going to the second, this is the second edge list, or second edge index, and I'm going to be looking at probability of success, the second one, which is this one right here, so 0.5, so 0.5, like that. So I'm just updating it. But now I also need to update that node 1 and node 2 are connected here, like it's the same connection, right? So no, this says node 1 is connected to node 2, but I also, node 1 is connected to node 2. So you have two connections, and because this is like an unweighted or undirected, there's going to be symmetry along this axis right here. Okay. So to do that, I can just copy and paste this. Okay. And then just change this to be 1 and this to be 0. And that way we're just getting the other index. And so the row becomes the column becomes the row. And so you kind of just flip those. Okay. So I think we have our adjacency matrix now. So now what do we want to do? We want to set that we needed a visited. So equals set. So we needed a visited. Okay. What is the other thing that we need? We need to set like the path to infinity. So I'm trying to think if we need a second adjacency matrix. Where initially everything is infinity. Possibly. So this and then infinity. Doesn't Python have like a INF? Like, no? Okay, whatever. We're just gonna set it to a large number. It's just gonna be like 999. Okay. For okay. So this is going to be the weight, the current weight from one node to the other one. So this is how I know if they're actually connected. This is going to be like not from one node to the other one, but actually the entire like weight from the start node to the end node, or to that specific node. No, maybe I just need like a adjacency list in this situation. So like do a path equals and then a list. Oh, actually, yeah, this doesn't even create a matrix, but it does like actually, okay. That's not even a matrix right there, but I can like path, yeah. Like this, and I just currently to visit node 0, there's a weight of 999, and then I just continue. I only need one index, or I don't need information from one node to another node, so I don't need rows and columns. I just need one like actual index, and that index is going to tell me, it's going to be assumed from the origin to that particular node. So from the origin to 0, like what's the current shortest distance? And the shortest distance right now is infinity. Okay. All right. So we have our visited. Good. Now what do we want to do? We initialized everything to 0. So now we do our start. Where is start is just an integer, and it is the like node, the index of the node. Okay, so path indexed at start equals 0. So the weight so we're going to visit the first element. We're visiting element 0, right? Node 0, because that's where we start. And so the weight to get to start is 0, because we start at 0, and then we're going to just accumulate that weight. Okay. So then we also need to add start to visited. So visited dot add start, so node 0. Okay. Graph traversal. We need to traverse this graph somehow. What are our methods available to us to traverse a graph? We can use a stack, right? Now we're doing kind of that depth first search, breadth first search, like just a pure traversal, right? So we need like a stack to be able to continue. Okay. So maybe I don't need this yet because I want to put that in the algorithm. So I need a set that tells me what, so my stack equals here, and then my stack dot append start. So I put start in the stack, and then I want to continue through my stack, and I'm going to continue to add values to my stack as I see them. I'm at my starting point, and I take my little binoculars and I see, oh, I see 3, I see 2, I see 8, I see 9, I see 1000, node 1000 way over there. I check all of my connected ones. I put that into the stack. I also process it according to Dijkstra's algorithms. Dijkstra's algorithms, like process or whatever specifications, the algorithms uh, procedure. There we go. And then from that, I'm able to then go up to the net. I'm able to go up to the next element in my stack. No, because uh, procedure said you have to visit the next lowest unvisited. Ah! Oh my gosh. How on earth am I going to keep track? I need to like sort it. I need to sort it for the every single time I need to go through this path and check the lowest number. That's not efficient at all. And then I need to check not only the lowest, but then I need to go and check, oh, is it invisited? Is it invisited? Is it invisited? Is it invisited? That's horrible. That's a horrible time efficiency. That must not be the way to actually accomplish it, but that's the oh. I was thinking about like doing while stack and then like uh, node equals my kind of like this, like my stack and then my stack dot pop. But that is not in accordance with what the algorithm says that we need to do. The algorithm says that we need to go to the well, what if I just have like a scene and then I have no idea what I'm doing right now. Scene dot append start. I mean, this is literally what I'm doing here. It's just a stack. Okay. So maybe I can do like my stack, and then I just traverse my stack. So whatever. For items in my stack. So I can find the current lowest, but I also need to be able to determine the... If item... What is item? What is it indexing? Man. I can feel my brain starting to kind of like shut off right now. Like, I've been doing this for a little while, and so my brain is like, I feel like it's starting to shut off. It's moving much slower than when I first started this video. Just trying to get past that finish line. Come on, brain, you can do it. You can do it. I had some like sugar or something. Give it some brain power. What am I even trying to do right now? I don't even know. 4 items in my stack. So my stack represents an edge. All of the nodes that I visited, or that I've seen. Okay, so will be an edge. This is like 0. Okay, items is 0. So and now I need to check the weight, right, in path, like the lowest. Okay, so if item is less than current lowest, then I want to update current lowest with the weight of the node that I'm considering to go visit, because right now I'm trying to figure out which node. I just visited one node and I saw these 2 nodes, and now I'm trying to determine which one I want to visit. Like, do I want to visit this one or do I want to visit this one? I need to go through and figure out, like, lowest path equals path item. Okay. So I'm selecting a node. Good, I guess. So then I say, hey, that's my node that I want to visit, and then I just keep changing that until I reach the actual lowest in my stack of like scene. So now I need to go and check the weights, or like update the weights, right? Okay. So how do I update the weight? It's gonna be in path, so what would that be? Path of so I need to check. I'm at a current node. I need to check all of the nodes that I'm connected to. So for I need to just go down that. Check. Okay, so row 0 will represent all of the nodes that I'm connected to. In of node. Okay. What do I want to do? I want to update path. So path of connection equals path of nodes. So it's my current weight plus the weight from my current node to that node. So plus adjacency matrix of path to connection, but I only want to update if it's smaller. So if path connection is larger than this, then update it. Then do like then do this and say equals. Then update it, otherwise don't update it. Okay. Well, visited. Come here and we want to visit. So item, and then we also want to pop it from my stack, right? So can I do like my stack dot pop and then item, or remove maybe, something like this, and then I'm out of this while loop, so if path to the end node, so path to end is equal to 999, that means there was no connection, then return 0, okay, otherwise return path end. I highly doubt that this is. Do we want to try it? I don't think. How many errors do you think we're gonna get? Like syntactical and also just like in terms of the algorithm. Like, it's just come on. Yeah. Okay. Outside the bounds of the array. Okay. You were given. So we got. So we got this success probability. So where I'm indexing two places. I don't exactly know where the indexing problem is coming. I'm gonna guess it's just this here, index. Edges enumerate should be. What is the enumerate function? So maybe it's flipped. Maybe it's edges index. Tags for Python enumerate. Index fruits. No, so it is index and then the actual thing. So these two are kind of connected, so they shouldn't have an indexing error there. So maybe it's here. So -1. I don't. Okay. I don't think I did this correct. Because I need to build a secondary. thing. I only put one element there. I see. I only put one element in this adjacency matrix. So can I just go like for in range of n? So just like do a double thing. Let's just run it to even see if it like if it fails here. Okay, so it didn't fail there, so therefore I think this is valid and I did create it. So path start start is not defined. Should be. Start node, okay. Can I just like just do that? Okay. Slices. Connection, adjacency. Connection and adjacency matrix. Yeah, I need to index something else. What am I? No, that should be okay, right? So, adjacency matrix is a list of a list, and I'm indexing it at node. Node is going to give me all of the value. Oh, it's going to be a list. It's going to be a list. Connection. Connection is going to be a list, right? Yeah. It's gonna be like a list, so a list of a list, a list of a list. Connection is here. Man. Oh. For connection in. So this is, I'm just trying to go through like all of these, and I want to eventually index like 0 and 5, right? But I'm gonna get 0, 5, and whatever, like 999, something like this. So I'm gonna get 0, 5, 999, 0, 5. So I get a list. So now maybe I just need to do connections for connection in connections, and then just like tab that. Int object is not iterable. But then that wasn't an int, so there was something else. All right, I think I'm gonna have to take a little bit of a break from this. Yeah, I'm not exactly sure. I'm getting syntax errors, which indicates that I'm not setting up my adjacency list and adjacency matrix and edge lists and all. I didn't do that correct, and also I have zero idea if I actually set up the Dijkstra's algorithm correct. I don't know if I did that correct either. So we didn't even get to test the Dijkstra's algorithm part because setting up the syntax, or the, not really syntax, but just like setting up the data structures for graph traversal and stuff like that, it kind of got in the way, and we're making errors. But I think my brain is a little bit too fried right now to be able to continue. I'll probably go have, uh, can you call it breakfast? But it's I'll just call it the first meal of the day, and have some more coffee. Try to maybe relax my mind a little bit, and then come back and try to look at this problem again. So anyways, thank you guys so much for watching this video. I will be back in a little bit, and then I am going to try to solve this problem again. So there's going to be a second attempt. So far, I think this was a really good problem because I was able to learn a lot. It kind of helped me wrestle with those ideas of adjacency lists, adjacency matrix, edge lists, how to go about doing graph traversal, what it means to be a directed, like why can't we have the cycles, all of this kind of stuff. It was very good. In terms of heap, like, I, okay, why is this in the heap section? Um, Obviously, my methodology of study is I try to do one particular topic, and then in that topic, I learn as much as I can, and I learn that topic. I'm not learning graph traversals right now. I'm not learning Dijkstra's algorithm. So it's kind of not really what I'm supposed to be learning. So actually, on second thought, maybe I don't continue to do this problem right now because it's kind of like not spinning my wheels because I'm learning a lot, but I need to make sure that I prioritize my time, and doing a bunch of random things, although it might be interesting, it might be fun, doing a bunch of random things is not very conducive to learning in a systematic way. So I'm not learning Dijkstra's algorithm right now. I'm learning heaps. I can't I can't oh, look at this shiny new thing. Let me go do this. No, I need to be focused. I need to learn heaps. Then maybe once I learn heaps, then I can go do Dijkstra's algorithm and I can learn it in a systematic way. I go watch videos. What is Dijkstra's algorithm? How is it applied? I try to do it. And then I am able to practice it, right? So, yeah, on second thought, maybe I don't come back to this problem until I start doing Dijkstra's algorithm. But the danger in that is I need to make sure that I actually legitimately do come back to this problem because I don't want to forget about it, and then this kind of problem to come up, and then I'm like, oh darn, I wish I would have. And then I'm in the same position that I'm in right now, where I'm just like desperately trying to solve it, but don't know how to solve it. Um, because obviously, if this problem came up, and this pretend this video was the actual real thing, right? People are going to be looking at it and being like, okay, well, this guy doesn't know what he's doing, because everyone wants you to be able to just like, oh, I know how to do it, do it really quickly, because so anyways, I need to make sure that I do come back to this problem, but I'm not going to come back to it immediately because I need to be focused and I need to do things systematically. And that is the way that I'm going to make progress, not by doing one thing and then doing another, then doing another, just chasing random things. That's not the way that I want to do it. I want to be systematic. I want to move. I did depth first search, bam. And I got to a point where I felt okay. And I said, all right, at this point, I'm going to take some time off from depth first search and I'm going to move to a different topic. So that's the forgetting part. And then I'm going to focus on that topic, which is heaps. And then once I get okay at heaps, I'm going to go back to depth first search to do the learn, forget, and then relearn. So solidify it into my brain. Be very systematic. So moving forward, I'm going to continue with heaps and heaps only. Then I will try to make sure that I don't forget about this problem and do it again in the future. So anyways, thank you guys so much for watching this video. If you would like, please subscribe because that would be awesome. And I am going to continue making LeetCode videos every single day. Also doing projects in Java, JavaScript as well. So if that interests you, please subscribe. My name is Timothy Lee Grant, and I will see you. I'm still going to go take that little bit of a break and then probably be back either doing another heap video or doing a Java or JavaScript kind of video. So anyways, I will see you guys today, but in a few hours. So have a wonderful day, everyone, and see you later.